From the Spec Network, this is Fragmented, an Android developer podcast where we talk about building good software and becoming better Android developers. I'm Don Felker.
And I'm Kaushik Gopal.
Welcome to the show.
This episode of Fragmented is brought to you by Kobaton, empowering mobile developers. Kobaton allows you to test your mobile app on real devices. Now, this means that Kobaton is a mobile device cloud platform. They provide you with access to real devices so that you can test on the Android devices that you want and when you need them. This allows you to identify issues faster because you're testing on those exact devices. Furthermore, they also provide you with an automatically generated activity log that helps you identify and resolve your issues more quickly. You can test the way that you want. So this is a kind of a cool thing too. You can run your tests manually, or you can run them through an automated fashion with some type of script. So if you want to connect it up to your CI server, go ahead. Or if you just kind of want to run a few tests manually, that's also an option. Monthly plans start as low as $10 a month. There's no annual commitment required, and users can cancel at any time. Visit kobaton.com/fragmented to start your free 15-day trial and see for yourself. In this episode, Kaushik and I sit down and talk with Romain Guy, a software engineer on the Android team at Google. We talk about displays, such as the 120Hz display that was recently shown and talked about on the Android Reddit AMA that we mentioned a couple of episodes ago. We dive into GPUs and CPUs and various different tools that you could use to help profile your application. And we wrap up this whole talk with a kind of a deep dive into what's changed in Android O in relation to color. It's a very deep topic and one that's very interesting with lots of technical nitty-gritty details. We hope you enjoy. So we have someone special on the show today.
We do. We have this pretty famous and well-known photographer who knows like a thing or two maybe about Android too. I'm not sure about the latter part, but man, this guy's a really good photographer.
He is. He's always been on my my Chromecast, which is amazing. I see the title down there. You see the photographer's name, and comes to find out that he knows a little bit about Android too. So, without further ado, Romain Guy, welcome to the show.
Thank you, guys. Thanks for having me.
Thanks for the photos.
Yeah, the photos, man. Like, what's the story behind that? Like, because your photo, I mean, typically when you meet someone, you're like, oh, like, I'm interested in photography. Like, oh, yeah, some of your photos are good.
Pictures of
but
cats.
Man, when you look at your photos, like, I mean, sometimes I think the only reason they have you at Google is so that, like, the wallpapers, they need those pretty wallpapers because your pictures are, like, crazy amazing.
Well, thanks. I appreciate that. Well, actually, it's funny because for most of my life, I didn't like taking pictures. I actually hated taking pictures.
Oh, wow.
Yeah, I know it's weird. But it's when I moved to the EOS for the first time. I was at Sun Microsystems for an internship. That was in 2005/2006. That's where I met Chet, actually.
Oh, interesting.
And I didn't know anybody here, and I lived by myself. So I started like going on road trips every weekend. So I bought a camera because the American Southwest is just so beautifully amazing. And I started taking pictures, and I haven't really stopped since then.
What's your camera gear, if you don't mind me asking?
Yeah.
So right now I'm using, I have two cameras. The first one is the one I use only for landscape pictures. It's a Canon 5D SR. So it's a big DSLR. It's a 50 megapixel sensor. It's big, it's bulky. Like I have a giant backpack. It's 20 or 25 pounds of gear I have to carry around when it's safe to take it with me. And the other camera I use, that's my kind of day-to-day camera, candid photos, like street photo, or when I travel for work, like I go to a conference. It's a Leica M10.
Oh, wow, nice.
So it's very different style. It's completely manual. It's both the worst and the best camera I've ever used.
So enough about the camera talk here. Even though we could probably go on that for a long time, we were kind of kicked in the conversations with you over various different topics around hardware and displays and colors and all kinds of other kind of cool stuff that's out there. I know, Kaushik, you had some questions around this, and it was very interesting to you too. What made the 120 hertz display stuff interesting to you to want to bring Romain on the show?
Yeah, so it started like on a previous show, right? So one of the announcements, I think this was
Yes, that's right.
about the time like maybe Apple released like a display like on the iPads or something for 120 hertz, right? And then
Yes, the new iPad Pro.
yeah, the new iPad Pro. And so I remember like maybe it was on I think it was on Reddit where like, I think the whole Android O.
The AMA.
Yeah, the AMA. In that, one of the threads that came up was like Romain actually mentioned about like the 120 hertz display existing even before that, like with I think Sharp or something, right? And one of the comments you made was like, I mean, it almost spoiled you for life, right? Like having seen that. So again, like Don rightly mentioned, our understanding of this, at least like the hardware layer, is like very, very limited, right? So typically, I think it's maybe 60 hertz, which is what most screens might be using. But like clearly, you know a thing or two about this. So we want to ask you, like, hey, what exactly is this 120 hertz display? What does that mean for Android? Is this something that we can get? Like, how does one go about this? Like, why isn't this there already? Like, we have so many questions around this. So we thought like maybe you could give us like enlighten us a little as to why this is not just like a flick of a switch or something.
Why is it important?
Yeah, of course. So like you said, most displays, especially on phones, displays are at 60 hertz, which means the display will scan out the frame buffer 60 times per second. And that's why, we always talk in our performance sessions at Google I/O or various other conferences, we talk about reaching 60 frames per second.
Right.
It's because that's what the display wants. And it's important because there's also the concept of VSync, so the vertical sync.
Oh, interesting. Okay. Can you tell us a little about that? Like, I mean, how does like the vertical sync work?
Yeah, so that is very important, especially because Android has kind of always taken VSync into account. So the problem is, when the display wants to show you what's in the frame buffer, it has to literally, like I said, scan out line by line what's in memory. And that takes some time. That's not, that doesn't happen in an instant. And the time it takes will vary from display to display. So the problem is, if you do update the content of the frame buffer during the scan out, you're going to have part of the old image that's already on screen, and then you're going to have part of the new image appear where basically your write into memory will meet the read that the display is doing. When that happens, that's what we call tearing. And you've probably seen it in games before on PC or even consoles where, like, when you do fast motion, like move the camera, it looks like the image is split in half a little bit.
Oh, so this is called tearing, is what you said.
This is called tearing. And so one way to fight tearing is to use double buffering, which Android has always done. So the idea is that instead of writing directly into the frame buffer that the display is reading, you just swap between two buffers, because that's super fast, right? You're just swapping a pointer. So you redirect the screen to the new buffer. The problem is that when you do that, you still want to be synchronized with the display, because otherwise, if you try to swap whenever you're ready as an application, the display might not be ready. So then you have to wait for it to be done with the previous buffer. And you might have, that might cause jank. You will have uneven frame rate because, maybe one frame you're able to swap at the right time. Maybe the next frame you're swapping in the middle of the scan out, and the frame after that you're swapping even later. So the idea with VSync is the display sends the system this pulse, 60 times per second, saying, hey, I'm about to draw a frame, get ready. And that's when, we race in the applications in the system to get everything done in time for the next scan out. So that, that is not linked to the frame rate in and of itself, but it's an important part of what makes the experience smooth and jank-free. Because really the idea is trying to have a frame rate that's as stable as possible. Now, on top of that, when you think of the refresh rate, so 60 times per second, it affects what we call latency, especially the perceived latency. So when you put your finger on the screen, the touch panel itself, there's a bunch of electronics that have to read your input. They see your finger. They have to do some processing on it. They send all that to the system. We do some processing. We send that to the applications. We wait for the VSync. We update the views. We run the apps logic. We render into the frame buffer. Then we tell the window compositor to composite all the windows and then swap the buffers.
That's a lot.
Yeah. And you're trying to do that 60 times per second. So when you do that 60 times per second, the base latency that you can get if nothing else was happening is about 16 milliseconds, right? From the moment you touch the screen to the moment that you see something. Now, in practice, touching the screen and doing some processing there takes a few milliseconds. We have double buffering, sometimes triple buffering, so that's 32 or 48 milliseconds there. And then there's the time that it takes, for the actual photons to reach your eyes. So the benefit of using a high refresh rate display like 120 hertz or even 90 hertz, which are popular displays in VR headsets, is to reduce that latency. Because now, if a frame takes 8 milliseconds instead of 16 milliseconds, you almost divided the latency in half.
Right. So it's almost like you can't perceive that slight lag, if at all there was, like, because it's happening so fast, like, or it's almost like impossible for your eye to perceive that lag.
No, exactly, and that's why, like I said, that 120 hertz display have kind of ruined me, because when I first played with this sharp display, I was expecting to have to look very closely, to be able to even tell the difference. But it was so obvious as soon as I touched the screen, like it felt so much better. Because really what's happening is that the pixels, as you scroll, seem to be tracking your finger even more closely than they used to.
Oh.
And without, even if you don't know what's going on, like if you don't know like why the device feels better, like it does feel better. And everybody who tried that, I took the device around the office, showed it to a bunch of people. Everybody was impressed. And that was certainly my reaction with the iPad Pro as well.
So I guess like the question is, why can't we do that now, right? Like, what is the implication?
So we could. There are several reasons why it doesn't exist yet, at least not on most devices out there. Like I said, Sharp has been shipping devices for about a year and a half in Japan. You can order one and highly recommend it. They're awesome. So there are several reasons. The first one is not all display technologies right now can sustain that kind of refresh rate. So LCD panels are currently the panels that can do 120 hertz. OLED panels, which are extremely common, especially in high-end phones, and OLED has a lot of benefits compared to LCD, but currently they're limited in terms of refresh rate they can reach. So it's about 75 to 90 hertz that they can do.
Oh, really? Interesting. I never knew that. Oh, okay.
Yeah, different technologies, different trade-offs, basically. So that's one of the issues. The other one is simply the time that it takes to render the frames. So at 60 hertz, you have 16 milliseconds, actually a little less than that, to do everything in the app you have to do. At 120 hertz, now you have 8 milliseconds. Right. And we know it's already challenging to do 16 milliseconds. So 8 is, twice as challenging.
Right. Yeah.
The next problem is bandwidth. Because at 120 hertz, you need twice the amount of bandwidth compared to 60 hertz, because you're doing the work twice as often. And the problem is that on phones, the bandwidth has not really gone up for the past, I would say, like 5 or 6 years. We're still in the 20 to 35 gigabytes per second range.
Oh, okay.
And that's challenging, especially, if you're trying to do white color gamut rendering or maybe HDR for video, like those things also need more bandwidth. Or if you have, higher resolutions, let's say if you're a manufacturer and you want a 4K display, you're going to use twice the bandwidth for that. So the question is, do you want the bandwidth for more pixels, for more colors, for more frame rate, or do you want all of it? Of course, the answer is all of it. But the reality of physics gets in the way a little bit. And obviously, all this has an impact on battery because you're just doing way more work.
Yeah.
I had a quick follow-up. Like when you actually mentioned the word wide gamut display, I actually truly understand what it means now.
That's good. I'm glad to hear that.
Yeah. Thanks to, I think it was at I/O, right? Like you gave a talk on color. Like, we'll definitely add a link to that. And maybe if we get some time, we'll touch on that. But yeah, thank you for that. That was a fantastic talk. You went into the fundamentals, not just necessarily how it works on Android, but you gave the fundamentals as to why it matters. So
it's one of those areas where ideally any developer who does UI or any designer would know all those fundamentals, but it's a complex science and it's hard to find accessible information that's explained in plain English, really. And frankly, some of it requires to look at complex graphs or even a bit of math, but it's all easily understandable. It's just there's not many good resources out there to clearly grasp everything that's behind. But it's really not that complicated, when you only worry about the fundamentals.
It also was additionally helpful because you explained it for with the developer audience in mind, where this is what and this is the fundamentals, and so that was super. We'll add a link to that in the show notes for sure.
The 120 hertz display, so it refreshes faster. It sounds like that's something that would make games fantastic. Anything that you would want really responsive, better. Like if you're creating like a sampler app for like audio processing or anything like video editing, stuff like that sounds like it would work great. But for like general application development, which a lot of developers do, line of business applications, is this something that us as developers here on the front lines of development can optimize our applications for? Should we be using high-res images, vectors, or is there anything we can do to?
That's a very good question. And actually, if I take a little step back, there are some benefits beyond just the latency. So you mentioned video applications. It's actually great for video playback. Because one of the issue is a lot of videos out there, like movies in particular, are at 24 frames per second, which is not a multiple of 60. So how do you play back 24 frames per second on a 60 hertz display? Well, the answer is there's a technique called the 3-2 pull down, where you kind of mix and match frames. I don't remember exactly how it works, but it's like every 3 frames, you take 2 of the frames and you mix them together, you interlace them. It's complicated and it doesn't give the best possible results. So the huge benefit of a 120 hertz display is that it happens to be a multiple of 24. And that means you can play back those movies smoothly on those displays.
I got to go back and research this because I think this 3-2 pull down is what you mentioned.
Yes. And then similar or kind of related to the high refresh rate displays, there are technologies, especially on PC for gaming, called FreeSync and G-Sync from respectively AMD and NVIDIA. The idea is that instead of having the display drive basically give you the tempo, saying, hey, I need a frame now, you flip it around, and when the computer is ready to give the display a frame, then the display shows the frame. And the huge advantage of that is that suddenly you can display things at random frame rates. You can display at maybe 47 frames per second and will feel smooth because the display will not be, fighting with the apps, basically. And so that's very interesting for games or any really interactive type of application. And I believe that Qualcomm has a technology called Q-Sync. I haven't looked at it in detail. That does similar things on mobile. So it might be coming in the future on mobile platforms. It's going to be interesting to see if and when that happens. But anyway, back to your question about what you can do in your apps. It's the usual answer of optimize your application, don't do too much. Don't use too many views, be careful about the code you write. And really, if you look at, if you run systrace on your application and you look at what it takes to run at 8 milliseconds, you might be surprised. It's hard. It's difficult.
I can imagine. We fight to get down to 60. I mean, to support 60 frames a second.
Yeah, and it really depends on your application. Like if you have an application, like if you're working on an audio editor as an application and you do a lot of custom rendering of those waveforms, that might be more difficult than if you only have a recycler view and you're just scrolling a list of data where you prefetch everything beautifully. But all the tips and tricks that we've been talking about for the past 10 years now, they all certainly apply, and even more so than before, because reaching that 120 hertz is going to be challenging for some applications. Now the good news is, if you do miss the deadline for 120 hertz, you're going to fall back to 60, which is not so bad.
Okay, so that makes sense.
Kind of a win-win there. I do have actually another follow-up question from a few minutes ago. I didn't get a chance to hop in there. You said something that was interesting. You said LCD, and then you said, OLED, OLED. There's also something I can totally mess this up. I'm not a display guy. It's AMOLED.
AMOLED.
Yeah, AMOLED.
Mm-hmm.
Yeah. What's the difference between these different, acronyms in, respect to screens and hardware? And is it something that developers need to worry about?
It's not something. OLED versus LCD kind of. Now the AMOLED is kind of, you can think of it as a variant of OLED. So for all intents and purposes, it's pretty much the same thing. There's also something called POLED, P-O-L-E-D.
Okay.
So, like, and there's also other things that are not used in phones yet. For instance, I think Samsung has something called quantum dots, yet another variant of those technologies. The biggest difference between OLED technologies and LCDs. So on LCD displays, you have a backlight, whereas with OLED, every pixel emits light. So what this allows you to do is that when you want to display black, you can just turn off a pixel. So you get much better contrast.
Right. The true blacks is definitely one thing, right? Like that's like a common like ding against LCDs versus like OLED. Even though you mentioned LCDs can do 120 hertz refresh, but like they don't. The contrast, like you said.
Exactly. No, and it's funny because if you look at HDR TVs, for instance, some of them, like LG has OLED TVs, and they claim that they have an infinite contrast ratio. It's because if your black is really black, so 0, when you do the ratio, you divide by 0, which, is infinity. Which is, it's kind of true, but slightly misleading as well.
That's like a marketing gimmick.
But that's a big benefit. The other thing that OLED displays, and I'm not entirely sure why, like, it depends on, it's based on how they're manufactured and the technology behind it, but OLED displays are better at displaying wider color gamuts. So there's you'll find a lot more wide gamut displays that are based on OLED versus LCDs. There are wide gamut LCDs out there, definitely. Apple is using them, for instance, in their laptops and in their desktop displays. But pretty much all the Android phones with a wide gamut display use OLED. I don't know of any that's using an LCD. There might be, but there's just so many devices out there. There's no way for me to know.
The next thing that I wanted to like transition us into is like, we sort of like understand, you gave us like some good tips, right? I'm writing this down, by the way. One of the tips you gave is like always use relative layout, because that's how we get like, we reduce the number of like views, and like, that was a very famous recommendation by you, right? So
always be careful if you see the word always on.
Right.
Yeah, that's good. I mean, for folks that are listening, like there's like this running joke where do you even remember when it was? Like, I think it was like quite some time back. You gave like this
time ago.
Yeah.
That was probably 2008 or 2009.
Yeah.
That was a long time ago.
Early on.
There was a talk where like Romain essentially like showed the benefits of when a relative layout can make sense. But I think like at some point, like you said like, oh, okay, in these cases, always use relative layout. And I think like the internet took that to heart, or like at least the Android developer community took that to heart, and they started using relative layouts for everything. And that is actually...
it's true of so many things, especially in our industry, where every pattern or recommendation somehow becomes a rule or a law. It's like back then we had this optimization called the view holder pattern.
Oh yeah.
Oh gosh, yeah.
Something I also mentioned, because back then it was giving us, I don't know the exact details, but it was in the order of like 5-10 frames per second or something, which was a big deal. So of course today it probably doesn't even matter. Like, it's probably the noise. But it shows that when you see those, especially when it comes to performance, you should always first measure, then apply, whatever advice you heard, then measure again, and see if it still holds up, because it might not. And there's no reason to, be mad at the original advice, because it was probably true at some point in time. It's just things change, technology evolve. The phones we have today are so different, both in hardware and software, compared to 10 years ago. And even, at the CPU level, like I spend a lot of time with a friend and coworker of mine. We often like disassemble native code, and we try to optimize, C++ code down to the assembly level. And same thing, like you see advice from like 2000, 2005, 2006 that just doesn't hold anymore today. And you think that CPUs haven't changed that much, but they have. Compilers have evolved, like everything evolves. And there's so many things like that where async task is another example that people are using it for everything, and you're like, no, that's not what it was for. And the list is endless, right? So just think about what you're doing.
Yeah, no, that's golden advice. Like, understand what the advice is hinting at, and then try to apply that to
Yeah, and
Okay,
that's
so-
certainly something that we tried. When I say we, usually Chet and I, we try to convey in our talks. We like to explain, how things work in the under the hood, so that when we give you an advice, it's really what we care about is to make you understand how things are inside, and also to give you like enough insight that someday if you run into an issue, you might have, intuitions or the will to like go look at the source code or something, because the advice itself is not as valuable, I think, as knowing what to look for and when to go look for it. Because if you're just, using the public APIs and don't try to understand anything about what's behind, like you're going to be stuck one way or another at some point.
And I think it's important to even say that the tooling to even profile these things has changed over the years. And that kind of leads me to a quick question for you. If you were to recommend Android, and I'm not trying to make this as some blanket statement again, but if you were to recommend the current tools at this given time, what would you recommend folks to be using to profile their applications to make sure that they're falling within, certain boundaries for we can get 60 frames per second or better?
Well, it's kind of all of them.
Okay.
So the first one that I usually tell people to start with is systrace, because it gives you a view of the system and it makes it fairly easy to grasp where or when the problem happens in your application. It's kind of like a high-level view as an app developer. Then, depending on what you identify, you will turn to the new CPU profilers that we have in Android Studio that will show you method by method inside your code where you're spending most of the time. And then, there are still things like the layout inspector / hierarchy viewer that will, if you've identified that the problem is too many views, then you'll go use that tool. So it's really it's really a toolbox. There's not one magic tool that will give you all the answers. And I wish there was, right? But really, you have to know which tool to use when. But usually, starting with systrace is a fairly good idea.
Yeah, I just recently played with the new profiler, so kudos to you and the Android team and all the tooling team who put that stuff together. It's fantastic.
Oh yeah, it's all the tooling team. Yeah, they did a really good job. It's nice to see good profilers in the studio.
One thing you mentioned is you said you and a colleague of yours like to play with CPU and play at assembly level. I found one thing that in the early days that always confused me in my career as a programmer was the difference between GPUs and CPUs, right? And over time I've sort of formed an understanding. But I mean, given that you clearly know a lot about this, right? I want to ask you if you could walk us through where does the CPU fit in and where does the GPU fit in, right? What kinds of tasks fit in at that level? And as an Android developer, right? At what level do I have to worry about this stuff, right? Just out of curiosity, if I have a view that's rendering, right? I know at some point we are touching the hardware layer and we're heading into the GPU layer, right? But can you walk us through, give us a sort of overview of that?
Of course. Yeah, it's a good question, especially because over the past, few years, and I would say 3-4 years, the boundary has been fuzzier and fuzzier, especially on the PC and console side, where now we're starting to see game engines where they use the GPU more and more like a CPU, where they don't even use the CPU anymore to drive the rendering of a frame. It's not yet there on mobile, but it's gonna come someday. Yes, so on Android, we've always used the GPU since Android 1. At first, it was limited to the window composition, so Surface Flinger was the only component in the system really using the GPU. And in Honeycomb, we added the hardware rendering inside the applications. So at a high level, what happens when your app requests a repaint, so when you call invalidate, you get those callbacks in your views. We call the onDraw method. We give you a canvas, and that's where you do your painting. As far as you're concerned, as an application, that's when you do your painting. What we actually do is that we don't do any work right there. We just record all the drawing commands, everything that you invoke on the canvas. We just record those commands, and we store them in what we call a display list. Now it's called the render node in the internal implementation. And then when we know that all the views are done recording their drawing commands, we send them to the render thread to actually execute them. So we go through the commands again, and this time we turn them into OpenGL draw calls. Now, what's interesting is when you invoke an OpenGL function, there's for instance GL draw. There's a family of functions called GL draw something. Those also don't draw right now on most GPUs. They also record and get executed later. So there's a lot of differing of the actual work. And the reason we do that is because if we record all the commands, and that's why we do it, and that's why the GPUs do it, when we know that we have the complete frame, we can look at the entire frame and we can do a lot of optimizations based on that knowledge that we wouldn't have if we were drawing immediately when you tell us to. So a good example is something that we introduced in KitKat, where we see all the drawing commands that you need to render your frame, and we try to sort them to minimize what we call state changes in the GPU, because those are expensive. But we also sort them so we can batch commands together. So a good example is like, if you're in the settings application, there's a lot of text on screen. All that text uses pretty much the same font, it's the same font color, it's the same font size, all of that. So what we can do is instead of drawing 20 times, like once per list item, we can batch all those pieces of text together and issue only one draw call to the GPU, which saves a bunch of time because we only invoke the driver once instead of 20 times or whatnot. And the GPU does something similar. There's a lot of, except for NVIDIA, although it's a little more complicated than that, but the GPUs out there from ARM, AMD, and Qualcomm, they're what we call tilers. So the way they render the screen into small tiles. So for instance, they take a portion of 16 by 16 pixels, they render that. Then they take another square of 16 by 16 pixels, then they render that. And the reason they do that is exactly what I mentioned. They can do a bunch of optimizations because they know that in that particular tile, they can merge a lot of commands or avoid some state changes. So yeah, it's quite complicated under the hood, and really you reach the GPU quite late in the process.
Interesting. And one thing that you mentioned is the idea that where they're trying to ship as many commands and get it to run. I think part of that is because when you jump between layers between the GPU and the CPU, that is partially, relatively that's a costly operation. So you want to bunch up as many operations as you can and the GPU do its thing, right?
It's not necessarily about that as much as the fact that a GPU driver, it's less true about Vulcan, but with OpenGL, the driver does a lot of work on your behalf. Optimizations, like I mentioned, validation, error checking, that kind of stuff. So calling into the driver is a very expensive call. It takes a lot of CPU time.
Got it.
So the more you can avoid jumping into the driver, the more CPU time you save. And then we have what I mentioned, the state changes that are more at the software level as well, where you say, oh, now I'm going to do blending and I want to use this new shader. So the driver has to revalidate your shader. It has to change maybe some hardware registers. So there are some overheads there. And that's why you do, you try to sort as much as possible to avoid those changes. When you think about it, it's kind of like, network requests where instead of doing, 1,000 remote requests where you're going to request just a couple bytes of data and you're going to pay for the overhead of, the different network layers, you just want to do everything at once to go faster.
You said something a few seconds ago that piqued my interest, and that was the word Vulcan. What is this thing that is known as Vulcan? And
I think when Chet and Romain were doing their what's new in Android, and I remember in one of these talks, Romain mentioned Vulcan, and he was so excited, and then Chet was you're probably the only one in this room who's that excited about Vulcan.
Right, and and as application developers, you should probably not worry or even think about Vulcan. Vulcan is a low-level graphics API, so it's closer to the hardware than OpenGL. And in a way, it's so close that you don't get any error checking. So when things go wrong, then you're on your own. OpenGL, for instance, does a lot of synchronization for you. Let's say that I upload a texture in the GPU, and then I say, I want to draw with that texture. OpenGL will guarantee that by the time it draws, the texture is ready. There's an implicit synchronization for me, so it's super easy to use. With Vulcan, if I upload data to the GPU and I want to draw with it, I have to use my own, synchronization objects in the GPU, in the driver, to make sure that the data is ready. Yeah, and so it's extremely powerful that way. Also, OpenGL is single-threaded. The API is single-threaded. With Vulcan, you can use multiple threads. You can reuse state more than you can with OpenGL. So there's a lot of benefits when you work on engines or middleware. But it's also more complicated. It's harder to use. Just a hello world in Vulcan, if you search for hello world, you might be quite surprised and maybe even offended by the length of it. It is a lot of code. And for good reasons, right? Because it just gives you, it's more flexible. But yeah, it's more work for engine developers, which they love because, they can be more efficient.
You get closer to the metal, so to speak.
Exactly, yeah.
And I mean, by that same token, like even OpenGL, like you mentioned, single-threaded. This was not. I mean, at least, like, correct me if I'm wrong here. This wasn't like necessarily a deficiency.
The reason why it's not multi-threaded has more to do, I believe, with compatibility, backward compatibility, because OpenGL has been around since the early 90s, and at least on desktop, like the OpenGL 1, like you can still run OpenGL 1 applications on desktop. They will just work. Minus driver bugs or whatnot. So in a way, it's kind of impressive that they maintain that compatibility, but it means that they couldn't do multi-threading, and the drivers have become extremely complex. It's a giant state machine. It's the biggest state machine I've ever seen. And I usually joke that if Google ever wants to fire me, instead of firing me, they can just ask me to either write an OpenGL driver or make me write a C++ parser. Either way, I'm out.
Nope, I'm gone.
Peace out.
Yeah, too much work, too complicated, too hard. And Vulcan is kind of like, reimagining the rendering API for 2016, 2017, like what it should look like now. And I alluded to that a little bit earlier when I said that the boundary between CPU and GPU is getting a little blurry, where more and more the GPU is used to not necessarily do actual rendering, but to do computation. So we have the concept of compute shaders in OpenGL. There are also languages like CUDA or RenderScript that are really meant to do just computations. And there's a lot of things you do in an engine. For instance, I worked on a small rendering engine with a friend of mine, and we run computations on the GPU that have nothing to do with actual pixels. Like we're actually trying to find visible lights inside the view frustum of the player. So Vulcan in that regard is interesting because it takes that into account. It's modern graphics is surprisingly a lot more about data management than anything else.
Interesting.
Yeah, so you end up writing a lot of data structures and crazy algorithms to go through those data structures as fast as possible. But the biggest and to go back to your original question, like there are still like huge differences between CPUs and GPUs, and the biggest one is that the GPU is what we call massively parallel or embarrassingly parallel, and so sometimes
that's interesting. Embarrassingly parallel, I like that.
Yeah, and it's fun because you sometimes have to like rethink your algorithms to work completely differently on the GPU because they're really, really good at running in parallel. Like there was one, for instance, that I wrote originally on the CPU where imagine you have a 3D grid and you have spheres and you want to know what cells of that grid the spheres intersect. And because the grid is big, you have thousands and thousands of cells. What makes sense is on the CPU, the way you parallelize, you say, okay, run on each thread, put a sphere, and then you check like what cells does every sphere intersect. That works great, but in this algorithm, like it involved logs and mutexes, which is completely fine on the CPU. The same algorithm on the GPU, you want to avoid this memory synchronization. So what you do instead, you don't say, I'm going to run a thread per a sphere per thread. You're going to do it the other way around. You're going to say, I'm going to go through all the cells, and for every cell, I'm going to test all the spheres because there are fewer spheres than there are cells. So you want to parallelize on the cells because the GPU is really good at that. So you have to think differently. And then because you're thinking differently, like the way you pack your data in memory becomes extremely important to make sure that the GPU is not starved and like always running. But the good news is that you basically have no debuggers, so it's extremely difficult to run this kind of code.
Good news in quotes, yeah.
Yeah.
And I mean, these days, like there is like the common argument, right? Like for the longest time, people bet that like, CPUs were going to get incredibly faster. But like the thing that like folks didn't expect or sort of like, it crept on is like the parallelism of GPUs, right? If you pick a modern day computer, in terms of like the power, like the parallelization, like having more like GPUs in a core versus like having like a extremely powerful CPU, right? I guess like my question is like, how do you see that translating in the mobile world, right? Like, are we going to see similar sort of things? As like, I mean, obviously this is like some time away. I don't think like it'll happen anytime soon, but like, what are your thoughts around that?
Yeah, I mean, we're going to see similar things. The GPUs on mobile are getting really, really good. Like every generation, like the compute power we get like goes up significantly. I'm actually shocked by the kind of shaders we can run today on mobile. Our biggest limitation remains the bandwidth. We are several orders of magnitude behind desktop when it comes to bandwidth, and that's a severe limitation in what you can achieve, especially for rendering. Now, the fact is, there's also, GPUs are often touted as those magic beasts that can solve all problems, and that is certainly not true. Just to give you an idea, and I'm oversimplifying the problem, of course, but the way GPUs work is so they can run, a bunch of threads in parallel. So often we talk about a wavefront. So for instance, on desktop, you can have 64 execution units at the same time. So what those do is they all run the same program. So they run the same piece of code, but they run in lockstep. So if any one of them takes a branch, you have an if else. If any one of them takes that branch, it will have to wait for the other execution threads to be done with their branch before it can go on.
Mm-hmm.
And it's very different from a CPU where every thread, as long as they're on different cores, they don't have to wait for each other. So again, it's really, really designed for the very problem of graphics where that most likely all the data that's close to each other is going to execute the same instructions. And so that's why they're not meant or not good at running, general processing algorithms.
It's not like this parallelization machine that you can just simply throw things at. Like it is like a little more subtle than that.
And for instance, also because the way 3D works, GPUs care about floating points. So they're really, really good at doing floats. But they're not that good at doing integers. Actually, an integer division is incredibly expensive on a GPU.
Oh, interesting. Okay.
But that's what apps do, right? Like that's what you do in most of your applications. So again, they're extremely optimized for very specific tasks. And programming for one versus programming for the other is two very different things. But at the same time, the CPUs we have today, like have also gotten better. Now we have out-of-order execution CPUs. We have a lot of cores. The branch predictions are awesome. We have really big caches. The instruction sets, for instance, the Neon, you might have heard of that, like on ARM, to do like parallel. It's a form of parallel computing. It is also extremely good, and the compilers have become insanely good as well. So it's not like the CPUs are left behind. They're just good at different things.
On a different note, I wanted to ask you about is like, and we mentioned this previously in the, like, as we were talking about like color, right? This is, I mean, we'll definitely add this link to the show notes. It's a fantastic talk that you gave. And obviously, I don't think we're going to cover the whole thing. I think the listeners should just like go and watch that talk. I guess like my question that I wanted to follow up with you is, you are extremely excited about like Android O doing something right with color, right? So like, could you like, maybe give us like a sort of like rundown on why I, as like an Android user, should like be excited? Like,
right.
what has changed about the way the like color is like rendered with Android, right?
Yeah. So fundamentally, I think that's a problem that any Android developer has run into. The fact you take like 2 or 3 random Android devices and you put your app on all those devices, you run it, and the colors will be completely different.
Then QA comes after you.
Yeah, QA comes after you, or design. And it might actually be an issue for branding. I think it was Joachim Verges, who works at Twitch from the Vulcan Profane, who was telling me that they can't get their purple right on any device.
I guess
And
like
certainly
Twitch, Yahoo, some of those folks have that
Yeah,
problem, I guess.
and it's true, like, there are some brands out there where a single color, for me, Twitch is purple. Like I can barely remember the logo, but I know that they're purple. And it's a problem that we've had on desktops as well. And, especially as a photographer, I've always had this issue where you spend hours taking your pictures and processing them and tweaking them, and then you show them to friends and they look completely different. I swear they look better than that.
This is why you spend 4 hours early morning, like, camping at that place. Like,
yeah, exactly. So fundamentally, the problem, and if you want the details, there's my talk, but we don't have a way of capturing or recreating the visible spectrum. So all the visible colors that our eyes and our brains can perceive, we don't have the technology to capture and recreate that. So we have a limited form. We use we have the stress stimulus value. So we use RGB. It's one model, one way of representing colors. And in the space of visible colors, if you have 3 points, that basically makes a triangle. And again, I'm oversimplifying. And the problem is that every display out there has a different triangle, can represent a different slice of what we can see. And so then when we have those color values in our apps, typically we use 8 bits per channel. So we have 0 to 255 for red and 0 to 255 for green and for blue. The question is, when you say red equals 255, is which red are you talking about? What triangle are you in that visible spectrum? And that's the fundamental issue. Like we have this arbitrary encoding that doesn't have a frame of reference unless you have what we call a color space. And a color space is that frame of reference. And then there's a lot of math when we know the source color space in which you've picked your color, and we know the destination color space of your display. With a bit of math and magic, we can turn your color from one space to the other and preserve, most of the time, the original intent, and we can find like hopefully the closest color to what you originally wanted, and make it look like we have the same color on every display. And so what Android did before Android O was effectively nothing. So
it's almost like the keys are the same, but like the legend for like the map, it's almost like you have like the absolute values and you're just literally using the same absolute values from a different color space.
It's like if I told you, if I gave you directions on the map and I said, okay, so walk, 100 feet this way, then 200 feet that way. If I don't tell you what's your starting point, that's not extremely useful. The answer is always going to be wrong. So before Android O, what we're doing is, your red 255 would be whatever was the most red color that your display could do. And on LCD displays, most LCDs have very similar capabilities. Again, I'm oversimplifying, but most LCD displays are close to what we call sRGB, which is a color space. It's a very common one. But OLED displays, they're called white color gamut displays because they can represent more colors than this sRGB space. And sRGB is the one that basically you're most likely using if you're using a desktop or laptop for design. So what we ended up with was you pick your red on your sRGB display, like all designer picks that red, and then we effectively remap it to a red that's redder on an OLED display. It looks super saturated.
Right.
And in a way, that's also why, a lot of people like OLED displays because they feel, it feels like you have a lot of contrast and a lot of saturation.
It feels like the whole screen pops, right? Like it's like in some displays, like it feels like everything is just like so colorful, right?
Exactly. But the problem is that, sometimes it pops too much.
Yeah,
and,
exactly. Yeah.
And if you got their YouTube redesign recently, you're going to see that the red of their logo is even redder than it used to be. On an OLED display, it's really, really red. And the problem that we've seen is, over time, even without knowing it, developers and designers have desaturated their colors to adapt to the OLED displays.
Oh.
So now what you have is, so now we have the opposite issues where what used to be like popping colors on OLEDs are now muted colors on LCDs. And that doesn't solve anything, right? You just shifted the prime somewhere else.
Right.
And it's also difficult because that means for a designer, like, they design on their computer, then they wait for an implementation, and they look at it, say, that's not what I want. They have to tweak, and you're kind of working in the blind,
Right.
which is never ideal. So color management in O, the idea is that we want to kind of solve this issue. It won't happen magically, because the only way to solve it properly is that we need to know the color space of the display. So we need that display to be measured, hopefully in factory, per device.
Right.
And without that, there's not much we can do. If we don't have that capability, if we don't have the color space of the display, there's still one thing we can do that we do in Android O, is look at the color profiles of images. So images that have been properly handled come with that information about their source color space. And again, what we did in Android before Android O was do nothing with that information. Completely ignore it. So now what we do with Android O, at the very least, if we don't know what the display can do, we assume, because that's the only assumption we can make, we assume that it's an sRGB display. So we look at the color space information from the image, and we convert the image to sRGB. So at least if you have an image with a certain red inside, and then you have a red defined in your application, hopefully as sRGB, then they will match on screen where they used to not match. So we'll give you at least that. But there's still, O doesn't cover like everything that can be done for color management. For instance, we let you draw with those bitmaps that have a color space and that can be, more than sRGB. What we didn't do, because we just didn't have the time really, is give you the ability to do the same with the canvas.
Oh, nice. Okay.
Yeah, when you think about it on Android, like, you define colors everywhere, right? You have those color hints that you said, the background drawable color, the text color, the pen color, all that stuff. So this is assumed to be sRGB. So we would need new APIs in a future version of Android, hopefully, to let you give us a color with a color space, so you can tell us what is that color you're actually rendering on screen.
Right. So it's almost like you're providing also like that legend, that color space, like, the map, so to speak, that we've been talking about. So that's also provided. So like, the true translation can happen at that point.
Exactly. Right? And that becomes important because since we do have white color gamut displays, if by definition, by assumption, I would say, all the content is sRGB, because that's basically what the internet is made of, and we do the mapping correctly, like we do now, then you have all those colors that you can't reach anymore. Because remember when I said, like, you had that red 255, we used to map it to the reddest color, but now we don't do that anymore. So suddenly you have all those other colors we're not using. But with sRGB, you can't reach those colors because they're outside of the range that you can use. So if we want to give the applications the ability to make use of all those colors, we need to give you the ability to tell us, like, what color space you're working with. That's the important part. But it's less important for, images are the part that we solved, and that's where it matters the most. Mm-hmm. It's a little less important for the rest of the APIs. But now someone, probably will be me, will have to go through all the APIs that take an int and make a variant that takes something else to specify the color space along.
I guess given like you're like one of the people who work on the framework that care about this the most, like,
Well, it's not just caring, it's also like over the years, it's a kind of feature. It was interesting working on it because to implement that feature, I had to change the window compositor, the rendering engine, the loading of bitmaps, introduce new APIs. I had to change the tools that capture screenshots. I had to change the viewer in Android Studio. It touches everything. It's not necessarily a lot of code, but it's everywhere in the code base. And basically you're hiding that extra bit of information. Say, okay, now you have a color space. But when a bitmap is sent to another process, now we also need to send that along. So, it's pieces of code like this that you have to plug in everywhere. And for me, that was not too difficult because, I've been doing Android for over 10 years now. And I have a fairly good idea of where to go look for it.
Yeah, I was going to say, you know where to look.
Yeah, I know where to look. It's just a matter of doing it.
Romain, this has been this is so good. And I'm pretty sure we can go on for another 2-3 hours, but we know
Easily.
we gotta let you go at some point. But this is fantastic. This is thank you so much for spending the time.
Yeah, thank you.
Well, thank you for having me.
If folks want to reach out to you and maybe ask you a little more hardware questions and stuff, what's a good way they can do that?
So there's Twitter, where I'm easy to find, just Romain Guy, one word, first name, last name. I also have a website called curious-creature.com, and my email is on that website, just simply first name, last name at curious-creature.com. They can just shoot me an email. Hopefully I will reply. I try to reply to everybody, but I don't always. Sorry about that. But yeah, those are the two best ways to reach me.
There's an interesting story because I used to follow your blog, Curious Creatures, for a long time, and I didn't know it was actually you. Because I was just used to read the posts and see you, because at some points you also posted pictures and stuff there, right?
Yes, yeah. A lot of pictures.
Yeah. So I didn't know it was you for the longest time until I realized, oh, wait a minute, it's all starting to make sense in my brain. Don, if folks want to reach out to you and ask you about other color stuff and what settings you have on your phone and if you have flux turned on or night mode turned on, what's a good way to ask people?
Flux is turned on right now. I'm sorry, Romain. It's late over here, so it's on. But anyway, the best way to reach me is on Twitter at Don Felker. And what if folks want to talk to you about your various different GPU, CPU chit-chat? Kaushik, how can I get a hold of you?
The same as you folks, first name, last name. Kaushik Gopal on Twitter is the best way to reach me. Thank you all so much for listening. Romain, again, thank you so much. This was so enjoyable for us. All right, folks, we will catch you in the next episode.
Once again, we'd like to thank our episode sponsor, Cobaton, empowering mobile developers. If you're looking for a real device testing lab that allows you to test and identify issues faster, you want to check out Cobaton. Monthly plans start as low as $10 a month, and there's no annual commitment. Visit cobaton.com/fragmented to start your free 15-day trial and see for yourself.
That's it for the show, folks. Fragmented is hosted by Don Felker and me, Kaushik Gopal. We edit and produce all the episodes here on Fragmented. Sarah the Amazing Jackson from the Spec Network helps with production assistance and wraps our final mix. Our theme and ad music is by the national recording artist Blueprint from Weightless Recordings. You can find more Fragmented episodes at fragmentedpodcast.com. Thanks for listening, and we will catch you in the next episode.